So I'm going to talk about how to put 1 and 1, 1 plus 1 together. So I'm going to talk about how to put maximal extractable value, or MEV protection, on DAGs. I'm very excited about both enhancements and putting them together. So the first advance, which we just heard a lot about, is a recent wave of works that scale performance of the core consensus of blockchains using causally ordered, reliable communication transport. And luckily, I don't have to waste a lot of time of my 22 minutes to talk about that, because we just heard a talk about it. I'm going to slightly modify it, so I'm going to touch on it just briefly. The second thing that I'm going to put on top of it is mechanisms for protecting against these reordering attacks that extract value out of looking at transactions before the ordering is committed. And fortunately, I don't have to spend a lot of time talking about that either, because we've heard a talk this morning by Ari about this. So I'm just going to talk about the challenges of putting these two together. And the idea is that, first of all, it's not completely trivial. And unless you do it well and effectively, you're just going to shift bottlenecks from one place to another. So if you have high throughput transport that provides reliable and causally ordered communication, but a very slow MEV protection on top of it, then you really haven't achieved much. And you're going to be like this guy trying to push a wrong cart of innovation up a hill, a cart square instead of a cartwheel. So that's the challenge, and I'm going to present Fino, which is putting these two together effectively for high throughput. But let me start with a little bit of historical perspective. I'm going to go a little bit earlier than the previous talk, and it actually gives me tremendous satisfaction to do this historical perspective right here in Stanford, because just when this wave of causally ordered, reliable communication started, I was a PhD student presenting here at Stanford this decade of systems that were built by separating causally ordered, reliable communication with the premise that then building on top of this consistency, atomicity mechanisms would be much simpler. And this is work that Ken Berman and others at Cornell University started with ISIS. And then there was a whole wave of systems, piecing, trans, total, and so forth. And I gained my PhD working on some of these systems. And then I came here to Stanford, not to this room, but somewhere around here, and presented what was my PhD thesis research then. And I was slaughtered by David Cheriton, who was a professor here at the time, grilled with questions. And he went on after that, not just my research, to publish a paper called CATOX, Understanding the Limitations of Causally and Totally Ordered Communication, in the ACM Operating Systems Reviews. And shortly after that, Castro and Liskov published their work on PBFT, which was leader-based consensus and was at the time the most practical solution. It was two-phase, it was pretty fast, and it used this wisdom, this insight that a leader can drive progress very quickly. This was an insight that was used by Paxos in the benign setting, and Castro and Liskov carried it to the Byzantine failure settings. And for 2 decades, the community just left these DAG-based or causally based ordered protocols and focused on trying to scale up consensus protocols with Byzantine failures and with benign failures. And for about 2 decades, there were a number of advances. Some of them focused on optimistically linearizing the communication. Others focused on linearizing the communication during steady state period, but still when when the leader was replaced, it wasn't linearized. And then we came in 2019 with hot stuff, which was finally the first fully linear communication. And sort of that's where scaling up stops, because you can't do more than better than linear. And the community reverted back to, okay, what can you do when you've scaled up as much as you can go? Well, you can scale out. So now you can start parallelizing. And this started a wave that, to the best of my knowledge, started in 2016 with Swirl DS, with Hashgraph. And then there were a number of systems, Blockmania, Aleph, and so forth, and culminated in this recent work that put consensus in the partial synchrony model on top of a DAG, which is Bullshard. So now let's talk for a second about MEV. I'm a technologist. My technology is neutral, so I don't know if MEV is good or bad. But thanks to Ari and his group of students, not only do we know about this problem, but there are also bots out there that actually make use of this problem. So in the MEV Explorer down here, we can see some estimates of just ETH MEV exploitation, which exceeds by today $800 million, and that's a very conservative estimate. And so what is MEV? So they've defined in this paper, Flashbot, a profit that can be made through including, excluding, or reordering transactions within blocks. That's MEV. Whether it's good or bad, again, I don't want to make a call, but clearly the existence of flashbots and mechanisms that exploit it increase contention and congestion on existing blockchains. It does cause more pressure on fees and increase in fees. And in some sense, it causes consensus instability because it forces reordering on what validators can do. And so the question is, can you put methods for protecting the fairness of ordering, the ones that were already published in the literature, can you put them on top of very high throughput mechanisms like a DAG? And I'm going to focus on blind order fairness, which is doing a very simple thing. It commits to an ordering within each block while not seeing the contents of transactions, while they're still encrypted, and only after the commit is visible and observable, then opening them. But other notions of fairness can just as easily be implemented with the same mechanism. So for example, time-based ordering or timestamp-based ordering can just as easily be done. Other notions of fairness, like participation fairness, sometimes referred to as chain quality or other terms, that just says that every participant has, or the honest participants have certain percentage of contribution into the chain. Those are achieved for free by these mechanisms, but they do not provide MEV mitigation. So the main strategy to focus on is commit then open. So in order to explain how we do that, I need to very quickly revisit what a DAG transport is, then talk about the basic consensus protocol on top of which you add MEV protection, and then how to efficiently integrate these three. So that's quite a lot, and we have, I don't know, about 17 minutes left. I'll try to get through it. But even if I don't, let me flash the main takeaway from what is the challenge and how we get around it. So the main challenge is we have these view-based protocols. They order view by view a collection of transactions that are accumulated in blocks on a DAG. And we want to move as fast as the fastest quorum of 2f plus 1 out of 3f plus 1. We don't want to have to wait for stragglers. And in an asynchronous system, we don't even know if they're actually alive or not. So we can't wait forever for more than 2f plus 1. But the problem is that all known mechanisms for blinding and unblinding, or blinding and opening transactions with 2f plus 1 fastest are very slow. And the fast cryptographic protocol will not move as fast as the fastest 2f plus 1. So this notion of responsiveness, that you can move and advance the consensus, the distributed protocol at the speed of the fastest 2f plus 1 breaks if you try to make use of the most efficient cryptography. And so what we do in Fino is a hybrid strategy where in optimistic mode, we use fast cryptography, and we fall back to slow cryptography if that fails, if we don't make progress after a certain period of time. Because everything is transparent and open on a DAG, this is relatively easy to see. Okay, so let me very quickly talk about the DAG transport, which is the communication substrate that guarantees that every message enters the DAG only after its availability or reliability is guaranteed and non-equivocation. So only one version of the message from each sender can enter the DAG. On top of it, parties can build consensus just by looking at the DAG and interpreting it locally. And the nice thing about separating these two layers or these two components is that you can focus and optimize each one separately. So you can do the best networking and the best systems work that you can on the transport layer and make sure that it saturates the network and makes use of the entire network bandwidth. And you can work on consensus protocols and optimize them and adjust them and add functionalities like MEV or whatever. And you don't have to affect one another. So this is nice modular design that benefits. So the main API of this modular design, which is exposed by DAG transport, is a broadcast and a deliver. So a party can ask to broadcast a message by presenting some payload. It could be blocks of transactions or references to them, and any meta information. And the transport guarantees to spread that information. And at some point, upcall at other parties a deliver event that guarantees that when it is invoked, it is different from receiving. When delivered, a message already has the stamp of reliability and causal ordering. So yeah, so I already said that. The main properties that the transport provides is that the DAG provides this guarantees that once a delivery event occurs, it guarantees the reliability and causal ordering. So here's how the lifetime of a broadcast and delivery on a DAG looks like. So party starts by gathering some transactions that are to be ordered and to be committed, gathers them in a block, and presents them as a broadcast to the DAG transport. The DAG transport adds two things. First, it adds mechanisms for guaranteeing the availability and reliability of the information. And secondly, information about any messages that were delivered in the past. So this is the causal past of this message. And with these two mechanisms, the reliability and the causal ordering, when the message enters the DAG, it has both guarantees. So the DAG here in my pictures are also drawn in this very regular matrix form, but actually it doesn't have to be this way. It turns out that it is a very efficient and a very effective way to construct DAGs in some networks. But there's nothing in the protocols and in everything that I present from now on that really necessitates that, which is also a very nice way to present it on slides. But this is not a property that we need. So now let me talk briefly about consensus built on top of a DAG. So in order to build MEV protection on a DAG, we wanted the simplest algorithmic foundation that we can use in order to build the MEV protection. And of course, later you could take other consensus protocols or optimize or add features to it, but it's nice to have a basic baseline to work with. So we took the component that works only for partial synchrony model out of Bullshark and adjusted it so that, just like this nice animated GIF shows, you never have to wait and operate in this rigid layer structure. So what we need in our protocol is a mechanism that allows us to inject blinded transactions and also their openings in a way that is completely detached from the algorithmic foundation and optimize the DAG separately from the mechanism. So we took that component, but separated it and slightly adjusted it so that you never have to wait for the consensus to present messages to tell you when can you vote or when can you propose a message onto the DAG. And we ended up with a protocol that is quite possibly the simplest, in fact, subcomponent of consensus protocol that you can adjust on a DAG. Now, the MEV protection will work with other protocols, but that's probably the simplest way to present it. So here's what it looks like. There are messages that keep accumulating in the DAG, just broadcast by parties. And every party has a notion of a view. Every view has a leader that everybody knows. The leader at some point marks a broadcast message that enters the DAG as a proposal. And implicitly, this proposal is proposing the causal history of all of the messages that preceded this. So in this DAG, you can see leader of view number R marks a message as number R, and the causal cone of messages that preceded it implicitly become the leader proposal. Then when other parties see that proposal, they can likewise mark messages in the DAG as votes at any time that they're ready, at any time that they observe. Meanwhile, the DAG keeps accumulating messages and blocks. Once f+1 of these votes are collected, then a view can commit, and at some point later, the next view proposal arrives at the DAG. Why is this so simple, and why f+1 and not 2f+1? Well, because the reliability and the causal ordering of messages that enter the DAG already do all the work. They already prevent equivocation, they already guarantee reliability, and you don't need more than f+1 to guarantee the safety of the commit. Now, of course, there's an unhappy scenario where a leader is slow or unobserved or faulty, and you wait for a while and no proposal arrives. Well, what parties will do is they complain about the leader in this scenario, and when 2f+1 complaints arrive, that enables the next view, which then arrives. So in this case, view number R wasn't observed by 2f+1 parties that complain, and that enables view R+1. So finally, I get to put these two things together. So you have a very high throughput consensus ordering mechanism, and you want to do a blind commit and then open on top of it. So what we need is a mechanism that provides implementation for three fundamental abstractions. You want to be able to protect the transaction. Then once a commit has been observed on the DAG, you want parties to vote to reveal the content of the transaction. And then when enough parties vote to reveal, you want to reconstruct it. And the key insight is that we're going to use the view structure of the graph and the fact that everything is transparent in the graph and that you can see when something has happened to delay the start of the next view until reconstruct can succeed on all of the previous views. So now it's left for me to tell you how to implement these three abstractions: protect, reveal, reconstruct. So the first obvious choice is let's use threshold encryption. This works by having a trusted setup, having all the parties share a decryption key, secret key, S key, and then when users submit transactions to be ordered, they encrypt it with the public key, PK, and in order to open after a commit these transactions, the parties reveal their own decryption share in this threshold encryption scheme. So this works like this. Again, the same DAG. There's a proposal of a causal coin. There are enough votes to commit it. Parties reveal their shares, and that enables the next view and the next view also opens all of the transactions of the previous view after they've been committed. Notice that already here we're making use of the fact that we can inject multiple messages into a view whenever we observe the vote, and that will delay the next view. And that continues view after view. It also works if you happen to skip a view because the leader is faulty and there are complaints. There are no shares revealed. After there are complaints, the next view is enabled. And in this case, view R+2 will open all of the transactions that were proposed both in R+1 and in R. So this works pretty straightforwardly. The problem is that threshold encryption is quite expensive. It costs milliseconds to encrypt and decrypt. And this is per transaction because this is coming from the users. This is not from the parties that implement the consensus or the DAG or any of the infrastructure. So that will cap the throughput of the entire system at several thousands or hundreds per second. So the next obvious strawman is to think about secret sharing. So Shamir secret sharing, polynomial secret sharing is very fast. It's order of microseconds per transaction, and could provide us the throughput that we want. But the problem is that with Shamir secret sharing, when we have a view that has committed an ordering and we want to open, the participants, the 2f+1 participants that are trying to make progress in the DAG might consist of F that don't have a share, F that are bad and are not providing a share, and perhaps only one that actually intersects with the original sharing. Even if we had all the shares, the problem is that a bad user could a priori share sets of secret shares such that different subsets would combine and produce a different output. And it would not be unique. And so for all of these reasons, mechanisms in the literature use verifiable secret sharing. So right off the bat, when the user shares, they have to commit to what is the value that they're sharing, and they have to prove that each share that they're sharing is actually contributing towards that secret sharing scheme. That works. And in fact, I published several papers in this field, and some of the best methods known by now can do this and can do it even with linear transaction communication in this setting. However, it would still be the commitment and the proof would still be in the order of milliseconds per transaction, and the reconstruct would need to perform this linear communication in order to recover missing shares. So what we do in Fino is very simply, we combine these two. So every view and every transaction will now be using both methods. You'll encrypt a transaction, the user will encrypt a transaction using the threshold encryption key, and also secret sharing among the parties. And when the parties observe a committed block, then they first open the secret shares. And if that happens quickly enough, then the next view is enabled. And if they time out, they will then reveal the threshold encryption shares, the slow path, and enable the next view. I think I'm running out of time, but looking at the DAG, this looks like this. Here we have a view. It's committed to a block of transactions. When parties try to open the transaction, one of them in red here turns out to be a bad share. Another one just doesn't have the share, so it provides the threshold encryption share. At some point, you might time out and use the threshold encryption, but in a steady state, you're extremely fast. So to summarize and make Joachim happy, what we presented is Fino. It explains how to put high throughput, efficient MEV protection using blind ordering, blind commit, and then open on a DAG. And in the fast, happy path, it's extremely fast. It works in microseconds. And it avoids any modifications or any breaking of this very elegant separation between DAG and consensus. I just want to say that in general, I find this pretty exciting that now that we have a new generation of very fast, high throughput consensus mechanisms, to think about what happens to additional functionalities that you implement with these consensus orderings and make sure that we don't shift the bottlenecks there. So this has to do with things like execution, reconfiguration, scaling the number of parties using sortition techniques, and various other questions that we can now revisit. Thank you.